All right, guys, let's jump into lesson 3, properties of functions. So we're going to focus on continuity, which is a really, really big deal in calculus specifically. We're going to talk a little bit about asymptotes and then behavior as well. But in order for us to do this, we have to really understand what continuity is and its specific definition. So we're going to say the definition is that a function is continuous where x is a specific value if the limit, that as x approaches that value of a, the function of x is also equal to the function of a. So that's a lot of very specific math verbiage that you're going to want to be very, very accustomed to. That math verbiage is going to be very important. Okay, so let's talk about what this means. That a polynomial is continuous at all values of x. So continuous means I literally don't have to pick up my pencil. So for example, if I draw this graph here, we'll call this function of some value a. Whoops, that wasn't a very good, I don't know why it's doing that. A, that here's a. So if I follow this up, this point right here, we'll call that point a for its x value, and its y value is going to be f of a, whatever that value is, because we don't know it specifically. It's a removable discontinuity, which is also called point discontinuity, and it looks like this. So let's say, for example, we have this function, but at a, instead of going through it, there's actually this kind of open hole here, and then it does the rest of the function, okay? So at a, this value is f of a. It has an open point, which means it's almost continuous, but it has a discontinuity at that value of f of a. And this happens when we can cancel a factor or we can remove a factor, okay? So like if you can factor a numerator and denominator and it cancels out, that creates a point discontinuity. Let's talk about jump discontinuity. So let's say you've got a function, there's an open hole here and it goes down to the left, and then it starts back up right below it, and it kind of goes up and to the right, something like that, okay? This has a jump discontinuity because as we can see here, this value, instead of taking on the value here, it jumps and it takes on the value here, and then it goes from there. So that's what a jump discontinuity is. And what happens is it's when the function jumps to another function, like specifically in piecewise functions. So remember, in your summer work, you had some piecewise functions that you had to work on where we have specific functions for different values of x. And then infinite discontinuity, here's what this means, that there's a vertical break along some value of x, okay? This specifically, we see this usually for rational functions or functions that look like fractions with a variable in the denominator. So it would look something like this. Let's say at a, we have a vertical asymptote, and then the graph could look something like this, okay? This right here tells me this is a vertical break along it, and then we see at the ending as x is getting closer and closer to a, the function is getting closer and closer to that vertical boundary. But on the right side, as we get closer and closer to a like this, there's a big infinite discontinuity where they're not a small gap, there's an infinite gap in between them. Okay, so let's practice this. Identify the points of discontinuity, describe the type. So if I look at this one for part A, I notice here that it has a denominator. So remember, we can't have the denominator equal to 0. So I'm going to set this not equal to 0 and see when would that happen. So I know that I do not want x to equal 3. If I plug that back in, I can see I know x minus 3 minus 3 would be 0, and I can't have the denominator being 0. So this creates a vertical asymptote, which means that if it's a vertical asymptote, that's right here. It's an infinite discontinuity when we have a rational function. So this is called an infinite discontinuity. Okay, part B, we're going to look at this one. Anytime that we can factor something, I know I can factor this in the numerator, so I get x plus 2 times x minus 2, and we have just x minus 2 in the denominator. Here I see, whoops, I can cancel those two factors. So remember, this word of canceling tells me that we're going to have something that looks like this when we can factor or remove that factor. This gives me a removable discontinuity or point discontinuity. Okay, so we know the value of x equals 2 because of this is a removable or point discontinuity. Okay, let's talk about some asymptotes. So asymptotes are basically describing the behavior of the graph at the vertical or horizontal extremities. Okay, so we're talking about invisible boundaries that guide the rest of the graph. Okay, so if I look at this function, f of x equals 2x squared all over x squared minus 4 is shown at the right. So this is what we have here. Okay, we're going to notice as those values become unbounded, meaning as x approaches 0. So remember, as x approaches 0, that's going here. So f of x is doing what? It's approaching positive infinity, okay? Well, positive infinity along this value of y equals 2. So along this dotted line, we can see this graph is getting closer and closer to that y equals 2 value, okay? As well as vertical lines where x equals 2 and negative 2. So if I factor that denominator, we see we're going to have these vertical asymptotes, okay? So if I factored that, I'd get x equals 2, negative 2 and x equals 2. Those are also vertical asymptotes. For those asymptotes, we have to kind of describe what's happening to the function on the left side of that asymptote and the right side of the asymptote. Same thing here for this asymptote. We have to describe what's happening to the left side of the asymptote and the right side of the asymptote. So let's talk about what that kind of behavior could look like. So vertical asymptote, or when we're talking about horizontal and vertical asymptotes always look like a vertical line. So x equals some value of c where c is a constant, okay? The way that we get this is we're going to set the denominator equal to 0 and solve, okay? So the graph of the behavior will approach the vertical line at either increase or decrease without bound, which means it'll move forever. So how do we describe that? So we say that this limit as x approaches, so we say as, well, let's go back real quick, 1 second. We say the limit as x, this arrow means approaches that value of c, and then if it has a negative up next to it, we say from the left. Okay, the way that we would say this one here, because there's a pluser, we would say the limit as x approaches c from the right. Okay, so let's fill this in. So looking at this specific graph, I know that as x approaches c from, so in this case, this c is 3, okay, this value of c, and we're saying it from the left side. So here's from the left side. What is the y value approaching? It's approaching an infinity. This specific case is negative infinity, okay? But we could say, if we're looking for forever statements, this could be plus or minus infinity, and that this is plus or minus infinity. So these are vertical asymptotes here. Horizontal asymptotes always look like y equals a horizontal value of a constant of b, okay? The graph will tend toward this value of b along the line. It's possible to have a horizontal asymptote. We can cross it. So it is a boundary for the ends, but not for the middle. And we could say that these limits are at that value of b. Okay, so here's what we're looking at here. So if I'm just looking at this graph, okay, so if I'm looking at this y equals 1 horizontal axis, okay, so I'm going to put that right here. If this is y equals 1, that asymptote right there, As x approaches negative infinity. So where is this x approaching negative infinity? So that's following along this line going this way. What is f of x doing? F of x is approaching what? It's approaching that y equals 1 value. So we can say as x approaches negative infinity, it's y, or f of x, approaches 1. Okay, same thing here. If I'm looking at this asymptote, let's look to see what's happening as x approaches positive infinity. So as x approaches positive infinity, we're looking to see, okay, what are those values of x doing? Let's look to see what the f of x is doing, which is this graph. As x gets bigger and bigger and bigger to infinity, this is also approaching that y value of 1. So we say y approaches 1 as well. Now let's look at that vertical line. So here's my vertical line. I can say, well, if that vertical line is at x equals 3, we can say as x approaches 3 from the left, so we would say 3 from the left, so it means we're moving left to right, going to 3. What's happening to that function? That function is going down forever. So we could say f of x, or the y value, is approaching negative infinity, okay? And as x approaches 3 from the right, so that's from the right going this way, we're going to find the f of x. What's f of x approaching? It's going all the way up here. So we can say as x approaches 3 from the right, the y value approaches positive infinity. Okay, let's talk about oblique and slant asymptote. So an oblique or a slant asymptote is possible. So it's not just horizontal and vertical. Sometimes we have an oblique asymptote, and that's this slanted line right here. And as you can see, these graphs are here, and it's governed, it's kind of like a tilted H a little bit, but we can see that they're governed by this vertical asymptote and that oblique asymptote. And these oblique or slant asymptotes happen when we divide by long division. So here I can see I can't factor this. It's not going to cancel out, right? I know that in order to multiply to 3, it's got to be 1 and 3, and I know that's not going to factor with this -2. So what I'm going to do is I'm going to use synthetic division. So dividing by x minus 2 means I put 2 in the box. My coefficients are 1, -4, and -3. Bring down the 1, multiply, add down, multiply by the -2, add down, and we get -7. There is a remainder here, but this tells me that this is going to be x minus 2, which is our value of our slant asymptote. So that's our linear equation of the slant asymptote. Okay, next one. So how do we find horizontal asymptotes? The way that we find horizontal asymptotes is there's one of 3 cases. Now, this is a very specific thing, okay? So when we're talking about horizontal asymptotes, this only exists when we have rational functions, where we have some numerator function and some denominator function. So we're going to let the degree of the numerator equal n, and we're going to let the degree of the denominator equal d. Okay, so this is what we're going to practice here. So remember, the degree is the highest exponent in the numerator, and the degree is the highest exponent in the numerator. Okay, so here's the first case, that the numerator degree is actually greater, not greater, hold on, back this up. That the numerator degree is less than the denominator degree, okay? So when does that happen? What happens then? Then if this is true, then the line y equals 0 is the horizontal asymptote. For example, if you've got y equals x minus 2 all over x squared minus 6x plus 9. If I look at this, my degree here is 1, and my degree here is 2. In this case, the numerator degree is less than the denominator degree because 1 is less than 2. Therefore, the horizontal asymptote is y equals 0. All right, let's look at case number 2. It says that the numerator is equal to the denominator degree, okay? So then in that case, the ratio of the leading coefficients is the horizontal asymptote. So whatever your leading coefficient of the numerator is, we'll call that A, over the leading coefficient of the denominator is B, and this is our horizontal asymptote. So for example, if you had y equals 5 minus 8x squared in the numerator and 2x squared plus 3x minus 4 in the denominator. Let's compare. The numerator has a degree of 2. The denominator has a degree of 2 as well. So because the numerator equals the denominator, now we look at their leading coefficients. The leading coefficient is the number in front of the value in front of the leading term. So this is x squared, which is the highest term. This is x squared in the highest term of the denominator. So we're going to say, therefore, y equals negative 8, which is our leading coefficient on the numerator, all over 2, which is the leading coefficient of the denominator. And now we can simplify this. So we know the horizontal asymptote is y equals negative 4. Okay, our last case is when the numerator degree is greater than the denominator degree. Okay, this says there is no horizontal asymptote at all. So for an example like this, you could say y equals x squared minus 5x plus 4 all over x minus 1. If I look at these degrees here, there's a numerator of 2 and a denominator degree of 1, therefore the numerator is greater than the denominator, therefore there is no horizontal asymptote. All right, let's look at some examples here. So this is identify vertical or horizontal examples. So remember, in order to find the vertical asymptote, you set the denominator equal to 0. Say it with me. Vertical asymptote, set the denominator equal to 0 every single time. So now we're going to solve. Add 6 to both sides. Divide by 3, and we get x equals 2. So our vertical asymptote for this equation is x equals 2. To find our horizontal asymptote, we're going to look at what 3 cases we're looking at here. So go ahead and first compare their degrees. So if I look here, I know the degree here on the top is 1. The degree here on the bottom is also 1. So the numerator equals the denominator. If you look at that, that's case number 2. That means we're now going to look at the leading coefficients, which are here, is 1 and 3. So we go 1 over 3. So my horizontal asymptote for this one is the graph of y equals, or the line of y equals 1/3. For part B, again, if I'm looking for the vertical asymptote, I'm going to set the denominator equal to 0 and solve. I get x squared equals positive 9. If I take the square root of both sides, when I take the square root, it's got to be plus or minus. So we get x equals plus or minus 3. So this is your vertical asymptote. There's two vertical lines. To find the horizontal asymptote, we go back and we compare the degrees. Remember, this degree is 1. This degree is 2. So the numerator degree is less than the denominator degree. This is your first case scenario, which tells you that the line of y equals 0 is our horizontal asymptote. All right, looking at our third example. Okay, so looking here, I don't know what we can cancel, but this looks like we can factor. I know this is a difference of 2 squares. This is x minus 4 times x plus 4. And here, if you remember x factoring negative 28 and 3, I can make that positive 7 and negative 4. So this is x minus 4 all over x plus 7. Good news, these cancel. Okay, just so you know, by the way, when we can cancel this out, this also tells me there's a hole or a point discontinuity at x equals 4. So keep that for later. But as we move forward, this is what we're looking at for our vertical asymptote. So we set our denominator, or remaining denominator, equal to 0. So x plus 7 set it equal to 0. And we're going to subtract the 7. We get x equals negative 7 is your vertical asymptote. To look at our horizontal asymptote, go ahead and compare what's left. This is a power of 1. This is a power of 1. Therefore, the numerator equals the denominator degree. And once they're equal to, that's case number 2. So we're looking at those leading coefficients of 1 and 1. So we know the y value is 1 over 1, which is just 1 for our horizontal asymptote. Last example. Okay, number 1, again, the vertical asymptote is always set equal to, that's right, hopefully you're thinking it, 0. So we set this equal to 0 and solve. So subtract the 1. 2x squared equals negative 1, divide the 2. But here's the thing, can a squared number equal a negative? No, it cannot. So therefore, this is not possible. Therefore, there's no vertical asymptote because it's not possible. Secondly, our horizontal asymptote, we're going to compare the degrees again. So these are the same. So the numerator equals the denominator. In that case, it's the second case where we use y equals the leading coefficient of the numerator over the leading coefficient of the denominator. All right. So this is really, really important that you have these down in your notebook, that you have them accessible, and that you remember finding horizontal asymptotes are based on 3 specific cases. Okay, case 1, case 2, case 3, we're always comparing those numerator and denominator degrees. All right, let's talk about end behavior. Here's what I need you to do. You're going to flip your entire packet over to the very, very back page, okay? Flip your this over to the very, very back page, and you are going to you're going to take this on another page. So pretend like this is the back of your page. I want you to draw this completely on your own because this is a really helpful chart to remember end behavior. So here's your end behavior chart. Okay, make this nice and big on your paper. So in end behavior, we are comparing 2 things. Okay, so make this chart. You can make this one nice and thick here. So make this one thick and make this one thick. Okay, so the first thing we're going to compare is the degree. Remember, the degree is the highest exponent of that function. On the side here, we're going to compare the types of leading coefficients. So that's the value in front of that term with the highest degree. Okay, so in comparing degrees, you can either have an even degree, so that would be like a power of 2, 4, 6, 8, and so on, or an odd degree, which could have a power of 1, 3, 5, 7, and so on. You could have a positive leading coefficient, or you can have a negative leading coefficient. So remember, this is end behavior. So we're not talking about middle behavior. So there are 2 ends of a function. There's a right side and a left side. So I'm going to draw this little squiggly line in the middle of both that tells you we don't know what's going on in the middle. But if we're talking about the right side, it's going to be the right of this squiggly line. If we're talking about the left side, it's on the left. So here's what you do. Anything that's ends positively ends upwards. So if it's positive, it ends upwards. Even if it's odd, it ends upwards. If it's even, they match. Okay, so they're going to go this way. If they're odd, they're opposites. So it looks like this. Just roll with me, write this down. If something is negative, like this is, it's always going to end down, no matter what. Okay? If they're even, they match. So they're going to go both down. And if they're odd functions, they're going to be opposite. So this one's going to go this way. So how do I say what is happening here? For even positive functions, as x approaches negative infinity, f of x is going upwards to positive infinity. As x goes to the right to positive infinity, y is going upwards to positive infinity as well. Here, as x goes to the left towards negative infinity, y is going down to negative infinity, and so on. So how do we state this? So we say in limit notation, here's how to say it. Okay, there's 4 ways that we say this. If it's going to the left and up, we say as the limit, as x approaches negative infinity, f of x approaches infinity. So it's going to the left and up, okay? If it's going to the left and down, we say the limit as x approaches negative infinity, that means left, f of x is equal to negative infinity. What if it's going to the right and up. We say that the limit as x approaches positive infinity, that's the right side, then f of x is approaching positive infinity, which means it's going up. And finally, what happens if it's going to the right and down? We would say as the limit that x approaches positive infinity, that's how we say the right side, f of x is approaches negative infinity, which is how we say downward. So remember, x describes left and right movement, f of x describes the up and down movement. All right, let's go back to our regular page. So we're talking about end behavior now. So end behavior, we just had that chart, so try to go back and look at that chart to make sure that you know what we're doing, okay? So looking at, sorry, one second, here we go. So end behavior, once we finish this, we'll be done with part 1, okay? End behavior is talking about what's happening on the left and the right-hand sides as we go to infinity. So this says state the power function. So the power function is like the leading coefficient and the degree of your graph. Okay, so for example, this is my highest degree and my leading coefficient is negative. So my power function is a negative x squared. Okay, this tells me it's negative and even. So on my leading coefficient or my end behavior, I know that it looks like it's going down and to the right and also left and to the right. So we say as the limit moves from x is going to negative infinity, we're talking about the left side, f of x is approaching or equals to negative infinity. We also say for the right side, as the limit as x approaches positive infinity, the limit as x approaches positive infinity, it goes to the right, f of x equals also negative infinity. Let's talk about what's happening here, okay? Our power function, if I expand this out, this will be x minus 1 times x minus 1 times x minus 1. We're only really interested in what this first term is going to multiply to. X times x times x is going to give me a positive x to the third. So we know that we're positive odd. Remember that positive odd means that we're going up and to the right and then mismatched down and to the left. So we would say that the limit as x approaches negative infinity, that's going to the left, then f of x equals negative infinity because we're going down. And the limit as x approaches positive infinity, which is going to the right, then f of x equals positive infinity as well, which is going upwards. Let's look at this one. If I had to multiply this out, I would get negative 1/2 x cubed times x for my first term, which is a negative 1/2 x to the fourth. So this tells me my power function is going to be negative x to the fourth. This tells me that it's negative and even. Remember that a negative and even looks like it's ending up and it's matching. So we're going to say as the limit as x approaches negative infinity to the left, f of x is also going to infinity. And the limit as x approaches positive infinity to the right, f of x is also positive infinity up. Last one, we're going to distribute this through. We end up with 3x squared minus 3x squared times x cubed is x to the fifth. This tells me my leading coefficient and my power function is a negative x to the fifth. This tells me that it's a negative odd. So remember, looking at your chart, negative odd means it's going to go down to the right and mismatch up and to the left. So we're going to say the limit as x approaches negative infinity to the left is f of x equals positive infinity, and the limit as x approaches positive infinity to the right, f of x approaches negative infinity or equals to negative infinity, which is down. All right, that's all we're going to do for part 1. We'll start with average rate of change for part 2 next time.